More properties of the z-score distribution. When referring to the or the z-score distribution, we are talking about the hypothetical distribution of all possible z-scores. Past, present, future, universe and beyond. There's not one z-score left out. All right. And again, that is what we're talking about when we reference the or the z-score distribution. That means there's only one of them. How can you have more than one of these if the distribution, the z-score distribution, is a plot of everything? There is no other distribution. If you're talking about the z-score distribution, there's only one. Now, that's important because remember how I said the mean is 0, the standard deviation is 1, the variance is 1? How do we know that? Because there is only one of these distributions. And somebody who was very, very, very smart figured it out, all right, and said, well, it's easy to kind of figure out the mean. I could have done that, I think. I could have figured out the mean is 0. But whoever this person was who figured out variance is 1, standard deviation is 1, they must have been really smart because it's hypothetical, right? So they can't use the numbers. Numbers don't exist. But regardless, these numbers don't change because there's only one z-score distribution. Okay? Now, we often work with, samples, and we might have a sample of 10 scores or 50 or 500 or 5 million, right? When we are working with a sample of raw scores, we can convert them to Z, and we can plot that sample of Z scores. Do not expect that this sample of Z scores is going to be normally distributed. Why? Because you don't have all the Z scores. You only have a sample. So the sample of Z scores, that distribution, will not necessarily look like the Z score distribution. Unless, of course, what if your sample was normally distributed? Well, you're going to learn right now, if your sample is normally distributed, then if you plot their Z scores, it will also be normally distributed. You're going to see this. Don't worry. If you're scratching your head, I'm going to explain this. Okay, so let's say we have a raw score distribution. Let's say it's grades on progress test 1 for your class. All right, that's only a sample of Z scores. That in no way that's not all Z scores in the universe and beyond. That's just a sample of Z scores. When we take your raw scores, so the raw score for the class, we take everybody's score and we convert it to Z. It's like we are recalibrating those raw scores. Okay, let me repeat that. So you start off with a raw score distribution. That's the distribution of scores on test 1. Okay, we're going to convert each raw score to a Z. What have we done? We've recalibrated your test distribution. We've recalibrated the raw scores so that now the new mean is 0, the standard deviation is 1, and the variance is 1. So even with a sample, okay, once you convert all those scores to Z, it's going to take the mean, so your X bar, it's going to take the mean and make it 0. It's going to recalibrate it. It's going to take whatever the standard deviation was originally, and now it's 1. And if it's 1, that means the variance is 1. So everything gets recalibrated. It has to. If you're going to compare apples and oranges, you got to recalibrate all your scores so that they have the same mean, the same standard deviation, and the same variance. Once that's true, you can compare apples to apples, oranges to oranges. And I'm going to go through an example. Okay, so just hold up. Now, just because you've recalibrated your raw scores does not mean that you've changed the shape of the raw score distribution. In fact, the shape of the raw score distribution and how your z-scores will look for that sample are going to be identical. And this is my pinky promise, okay? I promise you, and you're going to see in one of your SPSS assignments, that just by recalibrating raw scores does not change the shape of the raw score distribution.